Thanks very much. So in this talk, I'm going to be talking about how browser vendors in general, and Brave in particular, are pursuing privacy protections at layers below the extension layer, and what kind of privacy gains we think we can gain by going deeper in the stack. So in a single slide, here's what I hope to cover. First, I'll take it as read that privacy is a mess on the web, and that we got to do better. Then I want to make the argument that most of the work that's being done that's practical in terms of protecting privacy has been focused at the extension layer so far. And then I want to argue that we can do better by pushing further into the browser, into the runtime, into the JavaScript engine, et cetera, to improve the privacy the browser guarantees, and that new browser vendors are making this possible. So the way I'll approach this talk is, first, I'll talk a little bit about kind of a folk history of how I think we got to this extension focus. Then I'll talk a little bit about some specific examples of privacy modifications or privacy improvements that Brave is pursuing that can only be achieved by going deeper in the stack, that wouldn't be available at the extension layer. And then at the end, I'll end with a call to action for ways that I think browser vendors in the privacy community can work together to improve web privacy. So first, how did we get here? So I don't mean this is a specific technical history, but at a high level, I think this is what happened. We have people who are extremely interested in privacy, and they do extremely hard work and extremely valuable work trying to improve the browser, but their interests are different from the browser vendors. Browser vendors have an extreme level of technical expertise in maintaining runtimes and ensuring correctness, et cetera. So these are both extremely technical parties, but they have divergent focuses. So what I think shook out is that the browser vendors agreed to give other people the hooks that they needed to try to pursue their goals. And these hooks have been quasi-standardized as what we call the Web Extensions API. And so the Web Extensions gives authors and privacy-interested people a limited set of APIs where they can try to make some changes without having to maintain the deep changes, the very technical changes that modify the runtime. In contra to that, the browser vendors can focus on what they know best. And so in a lot of ways, this has been a successful story. There's a long list of privacy-preserving extensions that have made things much better on the web. And it's an appealing story for developers as well. The Web Extensions API is much simpler to work in, much more pleasant to work in, and much easier to iterate in than working down at the C++ level where most browsers are implemented. And we have evidence proof of this too, that extensions are extremely popular and they have millions and millions of users. But there's a downside to this as well. Extensions only have so much understanding of the web page and browsing behavior, and with this limited perspective comes limited capability. So we're ceding some ground to what privacy improvements could be achievable. That's the primary problem, and then there's also performance issues with focusing on the JavaScript layer and the Extensions API. So what I want to focus on is this area of the graph up here. What kind of privacy improvements could we get to, or how could we improve privacy on the web if we combine the expertise of browser vendors with the privacy focus of the privacy community? So that's how I think we got here. Now I want to motivate this by talking about two specific projects that are going on at Brave, where we are achieving additional privacy by going deeper in the stack. So think of this as the kinds of improvements we can get if more people focus in this area. So the first project I want to talk about is something called AdGraph, which is a classifier for tracking and advertisements on the web. And the second one is something we call SpeedReader, which is a privacy-preserving reader mode. And I'll talk about these in order. So first, AdGraph. AdGraph is something that we've been working on at Brave for a while now. This is work we've submitted that's under review right now. But the problem it's targeting is we want to be able to block network requests that we think are going to cede or harm the user's privacy. And so you can think about this as sitting next to or alongside a number of extensions. These extensions are extremely useful, and they use well-known approaches. I'll talk about two different approaches in turn. But the goal of AdGraph here is both to be more comprehensive, but also to be more robust against evasion, a problem that we see increasingly in the tracking community or tracking libraries. So the first approach I want to talk about that AdGraph is going to iterate on top of is URL-based blocking. This is an extremely common technique that's used in extensions. AdBlock plus easy privacy is probably the most well-known combination, where basically you identify URLs that fetch some sort of privacy-harming material, and then you build rules that just say anytime you see a request that looks like this, don't fetch it. So for example, if we knew that example.org/tracking was a privacy violating URL, we might do something like never fetch anything that's called tracking.js. But this is a relatively fragile approach. We know that there's a number of evasions that we see being used today online. Some of these are to rotate through different domains, so you avoid domain-based blocking by just using DGA algorithms or things like this to change where you're getting your code from. You might move the code from a third party to the first party to make it more difficult to block just the tracking-related material. Or you might compose all the code on your site together, so you combine both the benign code with the tracking code, making it much more difficult to block using these URL-based approaches. The second approach that's fairly popular online is behavior-based blocking. And this is a good example of this is Privacy Badger shipped by EFF. And so the approach here is a little bit different. Behavior-based tracking attempts to look at the behavior, or the types of code, or the types of actions that code is taking as it's executing. It attempts to identify things that look very suspicious, and then possibly prevent that code from being fetched in the future. And so for example, there's ways of using the Canvas API and the WebGL API to fingerprint users. So a privacy-based approach might say, anytime we see a single piece of code using Canvas and in WebGL, we're going to treat that as very suspicious, and we're going to prevent this code from executing in the future. This approach is useful, but is also prone to evasion. This is done, again, in a number of different ways. One is, again, just to move the code around. So if you block the code when it's at location A, well, people will just move it to location B. A second one, and kind of more pernicious one, is to break the code up against multiple, or the suspicious behavior up into multiple different code units. So instead of having a single code unit that does several suspicious things, you might have 10 code units that do 10 different suspicious things, and that makes it much more difficult to classify by code unit. And then third is just as an artifact of how JavaScript engines are implemented, it can be very difficult to attribute what code is doing what things. And in V8, the engine that Brave ships with from Google, these are known as microtasks. And microtasks, just as an optimization in V8, it can be very difficult to attribute what code is operating and what code unit was the owner of that function. So AdGraph is an alternative to these systems. AdGraph is facing the same problem. We want to decide what network requests to allow and what network requests to block, but we do it in a very different way. Instead of using blocking based on URLs or blocking based on behavior, we want to instrument the browser in a number of different layers. We want to understand the network requests that are being made, the layout properties of the page, so those are things like the DOM structure and what code units, what JavaScript code is modifying that, and then things that are just specifically in the JavaScript code, so ways of doing deeper attribution than is possible in V8 right now, and understanding what code units launch other code units, that sort of thing. And then we compose these things into a graph, and we use that graph to inform a machine learning-based classifier to decide whether or not to allow a request to happen. So I wanted to make this more concrete with a specific example. Imagine a JavaScript blob that a web author dumps into a page. That code executes and fetches another piece of JavaScript that it appends following that. That JavaScript code reads cookies or some other sensitive information, and then pushes that into the URL of an image that it appends to the document. This is how a number of tracking or analytic libraries are implemented. AdGraph will implement this as the following. We'll first notice that a script element is created, and we'll notice that that script element created another script element. We'll also then notice that that script element modified the source of the URL, or the source of the script element, and then that script element fetched some code from somewhere else. We'll then notice that the script element created an image element, that it modified the source of that image element then made a request somewhere else. So by getting this kind of rich understanding of what's going on in the browser, it allows us to make more informed choices. So instead of trying to classify just based on the URL, or just based on what a single unit of code is doing, we get this much richer picture, which allows us to be more robust to these very kind of simple evasions. And the results of this so far have been very promising. We're able to replicate human labels of whether or not code is tracking related with over 95% accuracy. We're able to, because we're not susceptible to the kinds of DGA or other kind of evasions that current approaches are susceptible to, we're able to track or identify code that avoids other tools. We're also able to run very quickly by pushing things deep down into the runtime layer and not just operating at the JavaScript layer and the extensions API. We're also we don't have the fragility of relying on these static lists like EasyList and EasyPrivacy, which are very useful, but are also very fragile. And what I want to highlight here is that this approach wouldn't be possible by just focusing on the extension API. We wouldn't have the breadth that we needed to inform the graph. We wouldn't be able to reach down to the JavaScript engine to understand the interrelationship between code units, and we wouldn't be able to do this quickly. And if it's not done quickly, then users are not going to be interested in the privacy protections we can deliver. So that's AdGraph. Now I want to talk briefly about another technology we're working on called SpeedReader, which protects privacy in a very different way. So SpeedReader is additional research that we've been working on at Brave. And the way SpeedReader works is, at a high level, it also protects privacy by blocking network resources. But instead of trying to identify the network resources that are the resources that are dangerous, we instead invert the problem and just focus on the content that we think is useful to users, and we ignore everything else. So as anybody who's used a reader mode tool can attest, a large portion of every page is not directly useful to the user at any given time. There might be boilerplate like menus or animations, or things like videos that are playing on the side. That's not strictly needed to enjoy the content of the page. So the approach here is to focus on the good and ignore everything else, while AdGraph is focusing on the bad and trying to exclude that. So I want to explain how SpeedReader works by comparing it to the functionality of existing reader modes. So in existing reader modes, as they're implemented in most shipping browsers today, the browser makes a request to the server responds back with some HTML, the browser executes the page by fetching all the sub-resources in the page. Those might be ads, images, videos, things like that. And each of those are their own network requests, so each of those also pose some privacy violating risk. Then once those are executed in the page, the reader mode is usually operated by injecting some JavaScript into the page. The JavaScript understands what's going on in the page and tries to extract just things that it thinks are useful, usually by using some heuristics like link density. And then this extracted subsection is presented to the user as the reader mode version of the page. SpeedReader is different. SpeedReader starts off the same way by making a fetch to the server, receiving the HTML, but instead of rendering it as a page, we use a number of different heuristics to try to identify whether or not there's a useful subsection of this page that we think a user will be interested in. This is a machine learning-based approach using a large hand-labeled data set. And if we think there is likely to be some subset of the document that will be useful to users, then we don't render the page at all. We don't issue any network requests for sub-resources. Instead, we just do the extraction on the HTML itself and render that. And the net result of this is that we're doing dramatically fewer network requests to dramatically fewer parties, and we're not executing fingerprinting-related JavaScript code. If we don't think there's a readable subset, then we just proceed as normal. And the results of this are pretty tremendous, both in terms of performance, but also in terms of privacy protection. So on the top row here, we have measurements of just using a default version of Chromium and visiting a large number of pages. So just to pull out a couple of the numbers here, on average, our automated versions of Chromium would interact with with over 100 third parties in the average case, fewer in the median case, but still an enormous number of third parties, informing them or potentially informing them of the user's browser behavior. We also see that a large number of scripts are executed on a single page, 51 scripts in the median case, 24 of which are identified as tracking or advertising related using a number of filter lists. SpeedReader, because it doesn't render the page before it attempts to extract the meaningful subset, does far less communication with third parties. We see that in the average case, we're only talking to a single third party, meaning 62 other parties never learn about the first party communication. We don't see any scripts executed. We don't see any ad or tracking material fetched. So this isn't going to work on every page. Only a certain type of page is going to be amenable to this type of intervention. But for sites where this is useful, you can see that the performance and privacy protections are dramatic. And again, I want to make the argument that this is not possible by focusing on web extensions. Extensions aren't, most web extensions, or the most extension APIs as they're implemented in most browsers, don't allow the user to modify the page, or the extension to modify the page in real time. There are exceptions to this, but not in the common case, which means that most extensions don't have the vantage point to do this kind of work in general. Excuse me. And then also, because we're doing classification at a number of different levels, both whether or not we think there's a readable subset of the document, and then also extracting the readable subset of the document, there's a fair amount of machine learning going on here under the hood, and that's also something that we don't want to be doing at the JavaScript layer where we're blocking everything. So pushing it down lower in the stack ends up being vital to making this a useful tool. So far I've talked about how I think we got to this extension focus, and some benefit. I hope I've given some examples of benefits of moving beyond this extension focus. Now I want to make the claim that it's important that we keep pushing things further to protect privacy. So again, consider this region at the top right of the graph, where there's a focus on privacy-preserving extensions. Or sorry, where we can combine the domain knowledge of browser vendors with the privacy focus and privacy concern of extension authors. And the more we can focus up here, the more new browser vendors move into the space, the deeper we can protect users' privacy. So what's new now, or what allows this new approach is that there's no longer just 4 large browser vendors. There's a large number of new browser vendors that are moving into the space and are making these kinds of approaches practical. And this means that there's browser vendors who are willing and interested in working with you to take your complex ideas and maintain them over time. So if extensions allow you to take a subset of tools and share them with a large number of users, new browser vendors want to ship complex approaches to a large number of users. And not only are there new browser vendors that are of different sizes and different levels of aggressiveness, many of these new browser vendors are explicitly privacy focused. Brave is one of these, but we're far from the only one. And because we're smaller fish in a big pond, we're also extremely eager to work with researchers and privacy activists. And we're willing to take ideas that are maybe long shots and think about how we can actually ship them out to working users. So the thing I hope you take away from this is that if you have an idea, don't limit yourself to the extension API. Don't limit yourself just to the hooks that browser vendors provide to you today, but reach out to other browser vendors and work with us so we can help protect privacy for everyone. Thanks very much.